So we just started iterative methods, and then we saw how the computer iteration depends on the previous one. And this iteration, that was equation 2, will converge. That is number 2. This iteration is convergent. And now we talk about iterative convergence. That is different from the convergence for a finite difference method towards the exact solution of the PDE. So here it's iterative convergence, that is the convergence of the iterative method towards the exact solution of a linear system. And that means convergence means that the limit, as we let the iteration number go to infinity, and we look at our iterative solution, that is, these are vectors, remember, that should be equal to x. And x should be then the solution, A inverse B. And that should be independent of the initial, of the starting vector. So that is what we call convergence, iterative convergence. This is, the iteration is convergent if and only if the following condition is true, that is the spectral radius of this matrix that we had seen before, where I said don't compute the M inverse, just for when we do the analysis of the numerics, we don't need it. So that is the spectral radius, what we have here. We had already discussed spectral radius when we discussed, for example, the Rosanov method. And that is, in that case, the maximum of all eigenvalues, absolute value of the eigenvalues, lambda L. And these are then the eigenvalues of the matrix that we consider. That is, in our case, the matrix M inverse N. So that is meant by this symbol, spectral radius. So in that case, we have to analyze this, have to determine the M inverse and determine the eigenvalues of M inverse times N. And N, that was the matrices how we distributed A. So that is something that we have to check when we do the analysis for an iterative method. I'll come back to this later. There are some theorems about that, and I can already say now diagonal dominance will be the key there. And the convergence will be the faster, the smaller this spectral radius of M inverse N is. So if you have that close to 0, then you're lucky. M inverse N. The faster the convergence. For our discussion now, we shall make the following assumption. And that is not an assumption, it's just a way to represent the matrix. So suppose that we can write 3, that is the matrix A, as the lower part of A plus the diagonal part of A plus the upper part of A. So these are not LU decompositions, but if you imagine you have a matrix A, which has, say, a diagonal, and it has some lower part, and it has some upper part. Then what is meant by this, that we write it as just the lower part, plus just the diagonal, plus just the upper part. That is meant by So you have a matrix, and the L is all what is below the main diagonal. The U is all that is above the main diagonal, and D is just the diagonal. That is how matrix A can be written. That we shall use now. And the first method that we shall discuss is called the Jacobi method. In the Jacobi method, we choose in our iterative method with m and n, we make the following choice. We choose m equal to the diagonal, and we choose n equal to the rest. And we added m minus n, so that has to get a minus L plus U. And that for our system that we discussed, that was for our system, and I think that notation was 38, where we had the letter notation, P, E, W, and so on, in the previous section, previous chapter, we had the following. The diagonal is just the center coefficient, and only that is then taken at the new iteration level, k plus 1. And the other ones are at the old iteration level. That is the A capital W, phi W is at the old iteration level, the phi, the A, that is the coefficient AE, times phi E at the old iteration level. Because remember, the W will be on the lower part, will belong to L, the E will belong to the AE will belong to the upper part. So they are at the old iteration level. And likewise the S, the phi S, that is also belong to the lower part, and the AN, that will belong to the upper part. That is, they are all at the old iteration level. And we have then, say, some part from some uniform part of the source term. So you see, this method is very, very simple. We just compute the right-hand side with the old iteration values that we have in the beginning, our starting guess, and then we compute the value, the new value, just by dividing this by AP. So it's extremely simple. So this involves not the solution of a linear system, like doing a U decomposition or whatever. It is just computing the sum and divide by AP, and that's it. So this method is called, which is called point Jacobi method, because we do the operation on the point, in that case on the grid point P, point Jacobi method. So what can we say to qualify it? Well, if we apply it, it would be even slower than the one you have in skeleton. You would observe a slow convergence. But if you would try to solve it in parallel, it would be extremely nicely suited, because everything is independent, so you can put this on all the processes that you have, distribute it, and let it compute. They all compute and the new iterate, and it's independent of each other. So it's very, very easy to parallelize that. But it doesn't help too much, because it is it's really a poor convergence. But it is, anyway, it is an advantage. Easily parallelized. A step further towards a better method is then, after Jacobi, looking to the Gauss-Seidel method. So the name names you see here are names of the mathematicians who worked on this in the, I think in the 19th century. So, and the one that is corresponding to the Jacobi would be the point Gauss-Seidel method. And in that, if we do our choice that we distribute, say, the m that we take at the new iterate and the minus n at the old iterate of A, we would do the following choice. We would choose that m is now containing also the lower triangular matrix and the diagonal, and the n is just containing then the minus upper part of A. So for our system, that would mean the following. So for our system 38, we would have the following, that is, we would have on the right hand side the AP times the unknown at the new iteration level, k plus 1. And that is equal to the AW phi. Now we have to think about how we compute it, actually. So here we have to think about that. If you imagine our problem, we have here x, we have here the y, we have our cells with our equidistant bridge. So imagine we have derivative boundary conditions. So we set the boundary conditions so that they are already in place and so on. And then we compute first, say we compute the value in this cell here. Then we will use these boundary conditions, and in the values here and here we will use the old iteration. But suppose we have done that, we are then computing, say we want to compute now things here, then we will use already the new iteration here. That is the trick. In Jacobi we would use the old iteration, but here we use the new one that we already have. So imagine we have computed all the solutions, say in the first row, and we have computed this using the boundary condition, using this new iteration value here, and we are, say here. Then we will use here the new iteration from the west and the new iteration from the south. They are already available. So that means the western contribution will already be at the new iteration level. It is already available and we use it. That is the difference. Here it was available but we didn't use it. For the AE, that is the neighbor here, there it is not yet available. So there we have to use the old iteration, K. And then for the AS, the AS, we do the same. That is already available, so we can use the new iteration. And the A north, the phi north, that is not yet available. So there we have to use the old iteration and the uniform part of the source term. So the only difference compared to the point Jacobi method is that we take the values that we already know, we already use them simply. So that is the difference. So this is the difference. So that we use here the k plus 1 here, and we use it here. That is the difference. We use them because we have them already. So that, yes.
Is there a reason that you have the same subscripts at the time? Because you have EMS and
I simply forgot them. Thank you. So we just have to add them. So this is then the west, this is the east, this is the south, and this is the north. Thank you. So, and this is then just the difference. We use the iterations, the new iterations, as soon as they are available. And that is implemented in skeleton. In skeleton, we don't have south and north, we have only west and east. So when it is computing Aij, this is then the A minus 1, and this is the I plus 1, then the solution at Aij, or the phi ij, is directly overwritten. We get directly the new value. So that is the difference between the point Gauss-Seidel and the point Jacobi. So this is then called the point Gauss-Seidel. So that means they are the new iterations. Are used. That is the difference. As soon as they are computed. And that is then called point Gauss-Seidel. So 7 is called point Gauss-Seidel. So it has it's slightly better convergence, not much. Say you need roughly half of the iterations you would need with a point Jacobi, but so it is a little plus, very little plus. So it's slightly better convergence. Let's see. So a little better convergence than the point Jacobi. That was but it is as a big minus, and the minus, it is difficult to parallelize because it depends on each other. You can only go on to the next when you know the previous one. You have to do some other strategy to do every second or so to do some trick, but this is really a headache. But for our purposes it's nice because it serves, in our case, to show you that for scalar problems in one dimension, then it is best to use TDMA, Thomas algorithm. So, then we want to get to a method that we are going to use next. That method is called line Gauss-Seidel method. So this is the point Gauss-Seidel, where we just work with the unknowns in just one point. Now we work on whole lines. So line Gauss-Seidel method. Okay, choose in the iteration method 2, that is from either 38 or 39 or 40 in chapter 11, the following. So M, that is the matrix that we take as the new iteration, so the part of A. And there we take also, like in Gauss-Seidel, we take the lower part, the diagonal part, but now we take also the part that is coming from, I write in this form, from the minus AE. that is on the part of the upper. So that's directly adjacent to the main diagonal, and that is corresponding to the part that is coming from the C when we use the index notation. Then the C was corresponding to the AE. And the N is then corresponding to the AN, that is again corresponding to the minus G, that is the coefficient coming from the northern, regarding the northern points. So, if we do that, it means the following. So we take now more and more parts of the matrix implicit, but we do it in such a way that we can apply the Thomas algorithm now to get the solution. That is the catch. So if we do it, we get the following. Thus we get this 9a. If we just look locally at, and now I use the letter notation, we have minus AW, and we have, that is now the matrix that we have, just part of the matrix, minus AE. So that is the matrix that we are now considering, these coefficients. And they are then multiplying our unknowns at phi W, and they are taken at the new iteration level. Phi P is taken at the new iteration level, and phi E is taken at the new iteration level. So, you see what we do here. We take this here on the left-hand side, and we take this. This is the new thing, also on the left-hand side. So that is, and then on the right-hand side, we have just the rest, and that is similar as here. That is the AS times the phi S, and that is at the new iteration. We do it like here. Then we have the AN, and that is still at the old iteration. That there is no change. And we have the uniform part of the source term. So you see, that is the difference regarding point Gauss-Seidel. We take now the AE, and thereby we make this a linear system. We make it a linear system on just one row, say on one line where we go in the I direction. We have one fixed J, and then we look at the unknowns for that. And then we get a tridiagonal linear system for that line. Yes?
Shouldn't the S be in K, or is it K plus 1?
Where are you?
Right side of the equation.
AS K plus 1,
Okay.
AN phi N K SU.
Okay, sorry, it's okay.
So this is just the same as here.
Yeah.
There is no change. The change is this. This is the change. Only this. This is at the new iteration. And that makes it, here we could just solve it by a divide. We just need, this we know, we just need to divide. But here we get a linear system. That is the difference. So that is corresponding to, so that is or 9b. It's corresponding to that we get a system BAC. And then I call this phi j at the new iteration is equal to the right-hand side. And let's see, and that is equal to the, let's see, it's minus the fj that is coming from the southern points. And there we have the phi j minus 1, that is at the new iteration, that corresponds to this here. And we have then the minus, that is coming from the j, and that is coming from the northern iteration, and that is then taking the j plus 1, and that is at the old iteration plus the SU. So these are the, so this is the form that we have here. So let's see. So we can interpret it in these two ways, either with the letter notation or with the index notation. Remember, the B was coming from the A minus A W and the C from the minus AE. So that is the correspondence here. And this is representing a tridiagonal system on one of these lines here. And since we can use the TDMA, we can do the solution by that efficiently. Remember, we have, in that case, we set the boundary temperatures, so we have only Ni unknowns in the grid points on one line in the x direction, and then we can solve these. For each line, we have to solve these the unknowns by the Thomas algorithm. So we have to call the Thomas algorithm as many times as we have nj nodes in the y direction. So the matrix, and we have to do this here for all what I just said is important. That is for all these rows, for j from 1 to nj. That is what I just said. And in here, the notation is that the B, A, C, J is denoting. Now we don't need to take the boundary points into account. They will be taken into account by the boundary conditions that we have set at the boundaries. So we'll have here the A1J coefficient, the C1J coefficient, the B2J, the A2J, the C2J. And that will continue all the way down to B, Nij, and A, Nij. So that will go down like that. And the one here would be then the C, Ni minus 1. So these are tridiagonal matrices with the dimension ni by ni. The phi j is an ni vector that contains the unknowns phi 1j and so on to phi nij. These are the unknowns in one of these lines. And the fj, or the minus fj, that is appearing on the right-hand side is then containing the minus, and that is then the f1j, we have just a diagonal matrix fnij, and the rest is 0. That is taking care of the southern contributions, and the minus gj is then minus, that is taken of the northern contributions, the g1j to the gnij. So that's it. So what we are doing here now is we are solving then for our problem. We have again here what we're considering, our domain x and y. We have our cells. Well, we might add some. So what we do is we first solve for our unknowns in the first row. That is, we have the j equal to 1. So this is the j equal to 1. Let's see, j equal to 1. So then we solve here. We solve a linear system, a tridiagonal linear system here. So we apply the Thomas algorithm here. We use at the boundaries where we have them, and we use the old iteration value because they are the only thing that is available, except on this line. In this line, we solve the thing coupled. So then they will be updated. They will get, after one solve of the Thomas algorithm, they will get the new values. So they will be updated when we have applied the Thomas algorithm. But they have been using only the old iteration values here. Then we take j equal to 2, and then we solve the Thomas algorithm at this line here. But now we can use already the new iteration values from the south. But we still can only use the old iteration values from the north. So we call that sweep. We go up to j equal to nj. So we go up here in j. And then the boundary condition here, that is then taken into account in by the first row. They are all taken into account, these boundary conditions. But this boundary condition up is only taken into account when we solve here. And to correct for that, we reverse the sweep direction. So once we have done this, we do another iteration where we go down here. So then we start from j equal to nj, and we go down to j equal to 1. That is the name alternating Gauss-Seidel, line Gauss-Seidel. First we solve systems when we start from j equal to 1 to up to j equal nj, and then we have some new iteration values, and then we go down. And when we go down, it is just the opposite. When we go down, we know the northern values when we are somewhere, but we don't know the southern values. So let us indicate that. And in this way, we get the influence of the upper boundary condition more easily transferred down. So we have a better communication in this way of the boundary conditions to the whole field. So let's do that. So then we have this. And now and now what I just said, I write it to propagate the boundary condition at the top down in the domain. We alternate. Here we see the name alternating line Gauss-Seidel, the sweep direction. That means we choose, so we alternate sweep direction. We choose in our iterative method, where we distinguish between the m at the new time iteration level and n at the old one, we choose from, and that is say 38 or 39 or 40 if you like, in chapter 11, the following. We choose m now to be, now it is containing the minus AW. That is now the catch. And let's see, to think about it. Yeah. And now we choose the diagonal, and now we choose the upper. That is the difference. The AW would be part of the lower, but that is now included. And the part that we treat at the old iteration level is then, if you take it on the right hand side, is then the AS. And the minus AW, that corresponds in the index notation to the indices indicated by B, and this corresponds to the minus F. So, and then we get then the following. So if we do that, we get would be 11a, that we have now the minus AW, the center coefficient, the minus AE coefficient involved, and the unknowns are still the values at west, new iteration level, the P new iteration level, and the E at the new iteration level. And that is now on the right-hand side, we have now the AS, but since we are starting from the top now, this is not yet known, so we have to take that as at the old iteration level. And the A north, then that can be taken at the new iteration level. And the uniform part of the source term. So that is now what we get. And you see we get again a linear system. We have again X and we have Y. We have our grid. But now we are starting up here. We are starting up here, computing here by solving a linear system here. We use then the boundary conditions, and when we are here, then we can already use the northern values. They are available. The iterations are available. So they can be used when we do it here, but from the southern values, we can only use the old iterations. So then we do a sweep in this direction. So we go down here. So the J is then going from NJ to 1. We are reversing the sweep direction. But otherwise, things are just the same as we discussed. Not enough with that. We then do just the same thing for setting up linear systems in the J direction. Now we have done these sweeps in the X direction, going up, going down, and then we set up then the systems where we have linear systems in the Y direction. So similarly, so I skip here the 11b, that would be similar as we had before, just with the different indices on the right-hand side, like here. So similarly, as we have done now for the X direction, that is the sweeps where we have the unknowns in I, and where we let J go from 1 to NJ, and then reverse the sweep direction. We do it now that we define tri-diagonal systems which are involving the unknowns on lines with constant I. Here we had lines with constant J, J1 and so on. Now we have just the other way round. And let me just do that briefly now. So what we do here then is we have then our problem. We have our xy. We have our equidistant grid in x and in y direction. And now we start by I equal to 1. And then we get unknowns here, on this line here. So we solve then, we get a linear system in that direction. And we use the boundary conditions that we have available, in that case on the left boundary, and each time we get to the upper and lower, we take that also into account. And when we are then at, say, if we have computed this, so applied the Thomas algorithm, computed the unknown in this, on this line with constant, with I equal 1, and we are at I equal to 2, then we can use the values that we have here, and we will solve the system here, but we cannot yet use the values that we have here. Here we can only use the old iterations, but here we get the new iterations by solving the system. So we sweep then in this direction until we get to I equal to Ni, and then we reverse the sweep direction. So then we do the same thing. We get our equidistant grid, and then we start here. We start by I equal to Ni, and then we sweep in this direction. So we sweep here we go from the I equal to Ni, we go to I equal to 1. Here we went the other way around. So when we, for example, when we are here, we know then the new values from the right, that is from the east, we know, but the values from the west, we don't know. They are at the old iteration level. And in this way, we can easily propagate the boundary conditions that we have at the right to the left. Here we propagate the boundary condition from the left easily to the right. And this combination of doing iterations first in the I direction, starting from J1 to J to Nj, going back, reversing, also looking at systems now to the either in the J direction for I equal 1 to I equal Nj, and then reversing that direction. This combination of these 4 sweeps is called alternating line Gauss-Seidel method. That is one cycle of the alternating line Gauss-Seidel method. So that is the one that we are going to use. So that means we are then calling the Thomas algorithm each time we have to solve a system either on a line with constant j or on a line with constant I. Okay, I think we stop here.